Hello everyone, this is Mrs. Logus and I will be taking you through numbers 1 through 8 on this video. And first we're going to take a journey back to Unit 2. The first couple examples, especially, well actually really numbers 1 through 8 are all from Unit 2 and partially things that have not been tested yet. So this is going to be excellent for eventual final exam review. So let's get started. Given these three functions, f of x, g of x, and h of x, find each of the following functions. And number one is asking you to subtract the f function and the g function. This has been tested before, so I want to point out what I noticed on the last test. If you take the f function, 4x, and subtract the g function, 6x minus 9, what I have written here is not completely correct because you are subtracting the entire function, 6x minus 9. Which means that that negative must be distributed to both terms. So you would have 4x minus 6x plus 9. So my final answer, if I combine like terms, would be negative 2x plus 9. Please be careful about this on your upcoming test. Make sure that you put parentheses in when appropriate. Number two, this dot represents multiplication. So what this really means is that you're taking the f function and multiplying it by the h function, which in this case would be 4x times 1 over x. If you're multiplying, you could multiply straight across and get this to be 4x over x. The x's cross out, which means that you're just left with a single number, 4. Number 3 is doing a composition of functions. So we're doing h of g of x, which means that you're taking the g function and plugging it into the h function. And so I'm going to keep the h out here, but I'm going to take g of x and replace that with what it is equal to, which is 6x minus 9. So now, if I take this function and plug it into the h function of 1 over x, whenever I see the x, I'm going to replace it with the 6x minus 9. So my answer here is going to be 1 over 6x minus 9, which I will also write over here, 1 over 6x minus 9. Now, if I would like to find its domain, because this is a rational expression, I know that this denominator cannot equal 0. So if I solve this, 6x minus 9 cannot be 0. That means that 6x cannot equal 9, which means that x cannot equal 9/6, or if reduced, cannot equal 3/2. So that means my domain is everything but the number 3/2. So it would be from negative infinity to 3/2, not included because it cannot equal 3/2, union 3/2 to infinity. Number 4 is also a composition of functions, and what it means is you're taking 2, plugging it into the f function first, and then taking that answer and plugging it into g. So if I take 2 and plug it into the f function, here's what I technically have. I have g of 4x if I plug the f function in, but now I'm taking the 2 and plugging it in here. That's really g of 4 times 2, or g of 8. Now the answer is not done. The answer is not 8, because now I need to take the 8 and plug it into the g function, 6x minus 9. So this would become 6 times x, which is 8, minus 9, which is 48 minus 9, which gives me an answer of 39. Now for number 5, I'd like to do the same topics graphically. So if I looked at part A, what this really means is f of 4 minus g of 4. So remember, the 4 represents an x value, and f of 4 represents a y value. So if you go to the graph of f of x, this means that if I go to the x value of 4, the y value that goes with 4 is also 4. So this is really like the point 4 comma 4. Minus g of 4, if I go to the g graph, go to 4, the y value that goes with 4 is here of 0. So I'm really taking the y value of 4 minus the y value of 0 and getting a final answer of 4. The next example really means f of 3 divided by g of 3. F of 3 is really a y value. So if I go to the graph of f, go to the x value of 3, the y value that goes with it is 2 over g of 3, go over to the x value of 3, the y value that goes with it is 1, so 2 divided by 1 gives me an answer of 2. Part C is saying a composition of functions. So I'm going to leave the f, but I'm going to first figure out what g of 1 is. So if I go to the g graph, go over to the x value of 1, the y value that goes with it is 3. So g of 1 is replaced with the y value of 3, and now this y value of 3 becomes an x value for the f function. So I would go over to the x value of 3, go up, and notice that the y value goes with it is 2. Final answer of 2 for C. And lastly, part D is another composition, but this time I'm starting with the f function, inside out. I go over to the f function, go to the x value of 2, and notice that the y value is 0. So this becomes g of 0. So again, plugged in the x value of 2 into the f function, got the y value of 0. This y value is now an x value in the g function, so I go over to 0, go up, and notice that the y value that goes with it is 4. These are very good problems. They will help with eventual standardized tests. I think that these really show understanding of what you're doing. Numbers 6, 7, and 8 all have to do with inverses, and this is a topic that has not been tested yet. Find the inverse function and state any restrictions on the inverse. So if I would like to find the inverse, remember that what we end up doing is we ending up switching x and y. So to find the inverse, we need to switch the domain and ranges. So before we start that, I'd like to point out that this, before we move anything around, this is really a line that has a slope of 1/4 x and a y-intercept of 9/4. So if I drew a quick picture, 9/4 is like 2.25. So I would have an increasing line from left to right. So this would have a domain of negative infinity to positive infinity and a range of negative infinity to positive infinity. Now I know the question didn't ask for this, but it's going to help later on. If I would actually like to find my inverse though, the first thing I would do is replace f of x with y. The next thing I would do is switch x and y, and then I'm going to resolve for y. So if I do that, I would multiply both sides by 4, get 4x equals y plus 9, subtract the 9, and I would get that y equals 4x minus 9. So my inverse function is 4x minus 9, which is also a line that has a y-intercept down here at negative 9, going up 4 over 1, so it is also increasing. And so the question is if there's any restrictions on this inverse. In order to have restrictions, it means it would not pass the horizontal line test. So I want you to remember that with inverse functions, we need to think about the horizontal line test. Now, here's the reason I found the domain at the beginning. If your original function has a domain and range that are not restricted, it means that the inverse will have a domain and range that is also not restricted. So are there any restrictions on the inverse, which is also a line? No, there are no restrictions at all, because this inverse passes your horizontal line test. There's never a chance where the horizontal line crosses the graph more than once. Number 7, let's also think about what this graph looks like at the beginning, because it'll help later on. This is a square root function as a quick graph, a square root function that moves up 2 units, and so it'll look something like that as a sketch. So does this graph pass the horizontal line test? Yes, it does, which means that it does have an inverse. Like this one did pass it, so it has an inverse. Before I start the problem, the domain of this function would be from 0 to infinity, and the range of this function would be from 2 to infinity. This will help us later on with the restrictions. If I actually would like to find the inverse, because I know it exists, because it passed the horizontal line test, I'm going to replace f of x with y. I'm going to switch x and y around and resolve for y. So I would subtract the 2. X minus 2 equals the square root of y. Square both sides. So you would get that y equals x minus 2 quantity squared. So this would be my inverse. However, notice that the domain and range is not negative infinity to positive infinity. So it has me thinking that I might need to restrict this answer. Now, let's think about this graphically, what this looks like. This is a parabola that is shifting 2 to the right. So if I drew a quick little sketch, this is what it would look like. Does a parabola pass the horizontal line test? No, it doesn't. So I have to only pick a piece of this graph. For instance, I could take this red piece of the graph only, and if I ignore this piece here, this red piece would pass the horizontal line test. So my restrictions would have to do with this piece. And so if I am talking about what is left over, I'm only going to keep the piece of the graph where x is bigger than or equal to 2. Also, I want to point out that let's look at the domain and range of this red piece. If I look at the domain of this red piece, that is going to be from 2 to infinity. And if I look at the range of this red piece, that is going to be from 0 to infinity. So check this out. The domain of the original function is the range of the inverse. The range of the original function is the domain of the inverse. That completely makes sense to me, because if I'm switching x and y, that means that my domain and range is also switching. So if you think about it, the range of the original function is going to help me find my domain or my restrictions on the inverse. So my restriction could be written 2 ways. Technically, the restriction means that you're only taking the red piece of the graph. X is greater than or equal to 2, so it passes the horizontal line test. But in interval notation, which we've been practicing quite a bit this year, your restriction would be from 2 to infinity. Last question on this video, number 8, has to do with restrictions as well. So this one, though, says restrict the domain of the original function so that the function has an inverse. The reason that we have to do that is very related to what we just did on the last problem. If you think about what this looks like, it is a parabola again that goes to the left 3 and up 4. So if I drew a quick sketch of that, it is going to be a parabola facing upwards, but this parabola does not pass the horizontal line test, which means that I need to take only a portion of this graph, so it is a function, or excuse me, it does have an inverse, or passes the horizontal line test. So if I'm going to restrict this or only look at the blue piece, it looks like that only occurs -3 and up. So x would have to be greater than or equal to -3. And this relates to the domain of my function. The domain of the blue piece would be -3 and up. The range of the blue piece would be 4 and up. So my restriction here is from -3 to infinity. That's where the graph needs to exist. Now what I can do is find the inverse. So what I'm going to do for a second to save a little time is I would like you to pause the video. I would like you to find the inverse on your own, and I will have the work when you come back. Please pause now. All right, guys, so here's my work for finding the inverse. My final answer for the inverse was the square root of x minus 4, all minus 3. Feel free to look at my work here, see if you match it along the way. So this was my inverse function, which I wrote up here. Now, what I want to do again is kind of notice the domain and range of this function, how it relates to the previous one. This is a sketch of this graph. The domain of this would be from 4 and up, and the range would be from -3 to infinity. I again would like to point out to you that the domain of the original is the range of the inverse. The range of the original is the domain of the inverse, which means is the domain restricted on this piece, or what is the domain of the inverse? Well, that is 4 to infinity. And to save time, you could just say, I know that the range of the original is the same as the domain of the inverse.